Cascadia is a major weakness in the Earth's crust. Although the Earth may seem to be a solid sphere, beneath the oceans and continents it is divided into 8 major and many minor segments known as tectonic plates. Where they meet, they can grind and jostle against each other at fault lines, causing earthquakes. Geologists had long thought that the Cascadia fault line was incapable of generating a major quake. But Atwater's investigation has proved that it was highly active. The big worry for Atwater and the thousands of people who live in this region is that the Cascadia fault line bears an uncanny resemblance to another highly active fault line, the Sunda megathrust. It was an earthquake along this fault that was responsible for the Indian Ocean tsunami that killed nearly 250,000 people.
Where we get 2 tectonic plates coming together, such as in the case of the Indonesian tsunami in 2004, one plate pushes beneath the other plate and creates lots and lots of friction and tension and drags the upper plate down with it. And that process can take hundreds of years, even thousands of years. It's a very slow process. But eventually, the pressure of this one trying to push back up again wins, and it flips like that. And that creates a megathrust, a sudden movement of the seabed. And that's what creates a phenomenal tsunami.
2 factors made this Sunda megathrust earthquake so deadly. The first was its size. At factor 9.2 on the Richter scale, this was the largest in nearly 50 years. The second was that it took place not far below the surface.
When we're talking about a megathrust, that's really where the seabed is disturbed dramatically. Sometimes, if the earthquake is deep in the Earth's crust, then you see very little surface manifestation of that earthquake. If it's quite close to the surface or very intense, then quite often you'll see the seabed itself moving, and that's what creates a powerful tsunami.
Investigating the ocean floor after the quake revealed that more than 1,000 miles of fault line had fractured and sprung up by 60 feet. This massive jolt pushed up billions of tons of water, enough to cover Manhattan to a depth of nearly 5 miles.
The rift zone itself was about 1,000 miles long. We had this entire stretch of subsea moving, which creates a huge wave. So the whole thing was a phenomenal size, and certainly one of the biggest tsunamis in living memory.
Atwater's determined research showed that the Pacific Northwest was at risk from this level of devastation too. But he didn't want to unnecessarily alarm the coastal inhabitants until he had collected all the evidence he could. Atwater needed to find out precisely when this tsunami struck this coastline to see if there could be more. He first tried radiocarbon dating the soil along the Copalis River, but the result could only take him so far. They showed that the earthquake and tsunami occurred somewhere between 1680 and 1720. More importantly, Atwater still needed precise evidence of how big it had been. But so far, his investigation has uncovered 2 extraordinary facts. By unearthing the abandoned fishing camp, Atwater could see that a Cascadia earthquake here had caused the land to drop. The notch in the bank was proof that this same earthquake had generated a tsunami. But what these clues didn't tell Atwater was just how big the tsunami was. He had no way of pinning down the size of the threat to the Pacific Northwest. His investigation was about to take an unexpected turn, with clues coming from not only thousands of miles away, but also from hundreds of years ago. Japan has the oldest record of tsunamis of anywhere in the world. Samurai writings told of a huge tsunami in 1700 that had swept over the east coast of Japan. It hit without warning and destroyed entire settlements. Japanese scientists were baffled as to where this wave had come from. There had been no earthquake to warn the villagers to make for higher ground. The mystery wave was dubbed an orphan tsunami. Back in the U.S., Brian Atwater's investigation into the mysterious Cascadia earthquake and tsunami needed more evidence. He had no accurate way to pin down either the size or the date of the event. All he knew was that it had taken place sometime between 1680 and 1720. But Atwater's dates were a revelation to the Japanese scientists. Could this event be the birthplace of their 300-year-old orphan tsunami?
And they said, by the way, we have this tsunami we've been trying to find a home for in 1700. So we think your earthquake happened in 1700, specifically in the evening of the 26th of January, 1700, and it was of magnitude 9.
A Cascadia earthquake that produced a wave with enough power to cross the entire Pacific Ocean to Japan would have had to be a factor 9 at the very least. This is roughly equivalent to the enormous Indian Ocean earthquake. Earthquakes like this have so much power that they can send a tsunami across an entire ocean with ease.
The amount of energy involved is very hard to estimate. It's hard to put it into sort of terms that people can understand. We are looking at the phenomenal forces of several Hiroshimas, hundreds of Hiroshimas in fact.
But tsunamis are not just a very big wave, they're fast.
The big difference is the scale of the wave. It's typically 300 or 400 miles long. It's also not very high. When it starts off life, it's usually about 2 or 3 foot high, but it's moving very fast. It moves at a speed determined by the water depth. The deeper the water, the faster it moves. So in the deep ocean, this wave is moving at over 500 miles an hour.
Deceptively, as a tsunami speeds through deep water, it may appear completely harmless and scarcely detectable. Close to shore, the wave becomes a deadly killer. It is only then that a tsunami's true power becomes clear.
As the wave gets to shallower and shallower water, as it approaches a coastline, the wave slows down. The shallower the water, the slower the wave. So it goes from 500, 400, 300, 200, much, much slower. The back of the wave is still going full speed, and so the whole thing piles up. And that's why tsunamis are so destructive.
It is this immense speed and power that reveals how events here in Cascadia could devastate a coastal village in Japan. How an earthquake in Chile could decimate Hawaii. And how the Indian Ocean earthquake could kill almost 250,000 people. If a quake like this happened in Cascadia, the damage it would do to the Pacific Northwest coastline would be catastrophic. But to be sure about the scale of this threat, Brian Atwater has to be 100% certain that the dates of the two tsunamis were the same. After fully exploring the estuary of the Copalis River, he found one site that might hold the information he was looking for: a ghost forest.
This spruce root marks the remains of a forest that includes the ghost forest behind us, dropped down into tidewater during the Cascadia earthquake. This ghost forest is made up of the standing dead trunks of western red cedar, and they were killed on account of the land here dropping and then tides coming in and surrounding these trees and bringing in salt water.
This area would once have been covered with a dense forest. But today, only the bleached trunks of the rot-resistant western red cedar remain in place. When Atwater and expert tree ring specialists cut them open and studied the lines of growth inside, they finally cracked the 300-year-old tsunami puzzle. The dates of the Japanese and Cascadia events were exactly the same: January 1700. The Japanese orphan tsunami finally had a parent.
Maybe there's a certain amount of justice to it that a place that doesn't have written records has these outstanding geological records.
The link between the two events made it certain that the Cascadia earthquake had been at least an awesome magnitude 9. And ominously, it is almost certainly not the only time that Cascadia has rocked this area. Atwater believes he has found proof of a whole series of tsunamis stretching back 5,000 years. Each layer of sand in this sample represents a separate tsunami.
There are places at Cascadia where I've seen 9 stacked up in a column about 20 feet long. 9 buried soils, some of them coated with little sand sheets. And you know, you say, okay, it's not a question of if, but it's just a matter of when.
Atwater's tireless detective work alerted officials to the increased tsunami threat. As a result, the towns along the Washington state coast have been able to prepare for this potential catastrophe. If a Cascadia quake occurred, the first waves could arrive here in just 25 minutes. Tsunami warning signs line the roads, and sirens stand ready to warn of an approaching wave. The lives of thousands of people are safer thanks to the work of Atwater and to some 300-year-old Japanese writings.
This is a hazard that shows its face often enough for us to take precautions to fasten the seatbelt against it.
By dating the ghost forest along the Copalis River to precisely 1700, Atwater had the final proof that Cascadia was capable of creating a Pacific-wide tsunami. Uncovering the multiple layers of tsunami debris in the riverbank dating back 5,000 years show that monster waves have struck here many times. This is an ongoing threat. Atwater knows that another earthquake is due here, but he has no way of knowing exactly when. Back in the Indian Ocean, the site of the world's most lethal tsunami in 2004, one man has taken the investigation of tsunamis to a new level. He believes that he has found a way to make the Earth's fault lines give up their secrets and accurately predict when the next deadly tsunami could be on its way. The idyllic-looking Mentawai Island chain in Indonesia hides a violent secret, one that makes it today one of the most dangerous places on Earth. These islands lie directly on top of the Sunda megathrust, south of where the enormous Indian Ocean earthquake triggered the 2004 tsunami. The Sunda megathrust is one of the largest fault lines on the planet. Since it caused the 2004 earthquake, it has also become one of the most notorious. Predicting earthquakes here is tricky, but Professor Kerry C. has a good track record. He has successfully forecast 2 along the Sunda megathrust already. The key to successful tsunami prediction is to forecast when and where earthquakes will strike. And to do this, scientists must look into the past.
If you want to answer questions about earthquakes that only happen every few hundred years or a few thousand years, well, you've got to find some geological instrument that allows you to see those earthquakes.
Professor C has found an unusual way to unlock the secrets of the Sunda megathrust's turbulent history. Corals. These coral atolls are built from the limestone skeletons of millions of tiny creatures. Each generation builds on the remains of the last. Over time, the atoll gets bigger and bigger. As long as the corals remain underwater, they flourish. But once they're above water, they die. Earthquakes are responsible for killing all the corals stranded above water on this beach. This beach contains corals of many different ages. Altogether, Professor C has nearly 1,000 years of history at his fingertips. But to unlock the secret history the corals contain, he and his team have to take a less than delicate approach.
We're looking at a saw cut that we just made through a coral micro-atoll. And the great thing about this head is it records a sudden drop of about 1.5 feet down to here. It died down to here because the island rose. The new low tide is way down here. Everything that was so bold as to grow up this high